Thank you very much for the introduction and also for the opportunity to present some of our work here in this very nice workshop. So this is on applying ideas from stochastic thermodynamics to motile active matter, something that I've been interested in for quite some time. But before we jump in, let me acknowledge the group, and in particular the two gentlemen to the left and right of me, Josh and Robin, who have been doing all the work. And I would like to already point out now that Robin is going to give a lightning talk after the break today. Okay, so active matter has become sort of a very sort of loose term, but what we usually associate with this is the emergence of sort of collective behavior on large scales that's been determined through interactions and, in this case, self-propulsion or motility. So the examples of this range from biology, for example, here where there are cells that have some sort of internal flow that they generate, organize into larger structures, into crystals, which then again sort of have a dynamics on their own. You can make synthetic active particles, harvesting a wide range of physical mechanisms, how to implement directed motion. And also very interesting now is sort of applying these ideas to robotic systems where you would like to sort of implement programmable, robust behavior of units where each unit itself is error-prone, is subject to fluctuations and so on, but still you want to have, through sort of emergence of collective behavior, robust programmable behavior. And it's been a staple that these systems are out of equilibrium and that they somehow convert stored or environmental free energy into directed motion of their constituents. So there is no sort of symmetry breaking, no global symmetry breaking, but there is dissipation dynamics on the local scale. Here's another example. So we can now sort of prepare these systems with millions of particles. This comes from the lab of Denis Bartolo. And you can see here, and really an active fluid. This is millions of active particles, so-called Quincke rollers, and a setup on the centimeter scale. And you can see here, I hope you can see the video and that it doesn't lag. You can see here how sort of there's very intricate, complicated defect dynamics that in the end leads to sort of a rotation of the whole fluid, something which is not possible in equilibrium. Okay, so why stochastic thermodynamics? So the type of questions you might be interested in, you might be asked is, for example, what's the thermodynamic cost of such directed motion? How much energy do I have to provide to realize that behavior that I maybe see in nature? And related to this is, because you have to provide that energy and it's going to be dissipated, you could be asking yourself, okay, how much of this energy can I recover as work? And so there are a number of examples where people have used, for example, bacteria, a suspension of bacteria as an active medium. So this is work from almost 15 years ago where they put a cork into this suspension, and then due to the directed motion of the bacteria being trapped here in these teeth, you can observe unidirectional rotation of these corks. So these really go forward on average. Another example that has already been shown yesterday is a cyclic machine, a cyclic engine, where bacteria are trapped in an optical trap, and then you can change the stiffness, change the temperature or the activity, and sort of try to extract work from this. Another question is, very interesting question is, like, now that you have to provide energy and it's being dissipated, how does this dissipation restrict large-scale collective behavior? So this all seems to sort of boil down to an inference problem that we know from stochastic thermodynamics from now where you want to sort of estimate entropy production from observable data. But before getting there, you have to sort of define what are the expressions for entropy production. And this is where it becomes a bit sort of difficult, because you have to realize that a lot of these models in active matter, they're actually effective stochastic evolutions. So they come like something like this. We have a Langevin equation, so we know this part. There's a force, there is some noise that comes from the solvent. And now this is being augmented by a self-propulsion term. And this self-propulsion term is not constant, but has some dynamics associated with it. So this could be, for example, sort of a propulsion speed in a direction, but this direction has rotational diffusion with a correlation time to r, or you can let the speed fluctuate. And then you can try to sort of apply recipes from stochastic thermodynamics, for example, ideas from Sekimoto, that the dissipation is really sort of the force from the thermostat applied to displacing particles. And if you then plug in this equation of motion, for example, you get an expression like this. If you take the average, the last two drop out simply because this is in steady state and this involves the noise. And then you get, for example, an expression, let's call it QT, like thermostat, where you have the fluctuation of this propulsion speed, and you have to subtract sort of the force that acts against these active displacements, U. You could also look at this equation here and say, okay, I'm looking at the path entropy. So what's sort of the breaking of time reversal symmetry? We know how this works. So you have to identify odd and even terms. And then what remains is the product between odd and even terms. So if you say that, for example, the speed is odd, then you get something like this. You take the average, again, in a steady state, and you already see that this is different if it's applied to these types of equation, and this is different from what you would get from the dissipation through the thermostat. So you don't have this term, and at the same time, the minus sign, yeah, so there's a minus sign here. So at this point, one has to sort of realize that these effective equations of motion, sort of applying these recipes, gives you the reversibility that is intrinsic, but only to the effective equations of motion. So what these are missing is sort of what's the effect of any physical mechanism that provides the self-propulsion. Yeah, so it's agnostic to the hidden chemical degrees of freedom. But you might sort of wonder, what's actually the heat that I would measure if I could have like an apparatus like this, which is a calorimeter. Yeah? So you put your active liquid inside this calorimeter, and you're really able to determine what's the heat that's being exchanged with the environment, and what's the entropy that's being produced in the universe. And to do this, we sort of have to think about how the system is actually driven away from equilibrium. And this is by coupling of these active particles to reservoirs. And we know how to treat this in stochastic thermodynamics. And this is indeed sort of a valid picture. So here are two specific theoretic mechanisms for self-propulsion. So on the left, it's a colloidal particle, a Janus particle, has two hemispheres. And like on one hemisphere, you have you catalyze a reaction that goes from, let's say, substrate to product. So these are just two molecular solutes that you can convert. And if you build such a colloidal particle, and it has been done, then this propels forward. Another possibility are diffusiophoretic mechanisms. Again, the easiest is to have a Janus particle. And now this is surrounded by a binary solvent. So as you increase the temperature in the vicinity of the particle, what happens is that this binary solvent demixes. And also here we have a transduction of free energy. So what you sort of through this heating do is you take a parcel of the uniform solvent, you bring it into the two-phase region at phase separates, and then this liberates a certain amount of free energy per fluid parcel. And this is the free energy that is available to the colloidal particle to undergo self-propelled motion. So in both of these mechanisms, you see that we have, through a coupling to reservoirs, a transduction of free energy. So to sort of put this into a model that can be used by stochastic thermodynamics, it's instructive to look at how this is typically modeled. And this is typically modeled really from a purely hydrodynamic perspective, from a fluid dynamic perspective. So the typical approach is you have your particle, you look at the surface of the particle and the vicinity of the surface. There's a concentration gradient in the lateral direction, and you apply what's called the thin boundary layer approximation. And with this, you get sort of Navier-Stokes equation that you can solve and that give you the speed of the solvent, the flow profile of the solvent. And from this, you can then calculate by using sort of reciprocity, what's the speed of the colloidal particle. So this is not the ideal starting point. So what we did is sort of trying to find a model that is compatible with this picture. So the predictions are compatible with this picture, but it's also amenable to our stochastic thermodynamics approaches. And this actually looks very easy. So here we are back to a Janus particle. So the orientation of the particle is along these two hemispheres. And now on one side, we allow a catalytic zone in which substrate molecules are being converted into product molecules. So this happens only in this zone, and then they diffuse outside the essentially ideal gas of substrate and product. So to check this in computer simulations, we cannot go to infinite systems. So what we do here is essentially sort of having a chemiostat. So outside a relatively large radius, we sort of convert these two species into each other with another set of rates so that we clamp the concentrations of product and substrate far away from this colloidal particle. And so specifically the rates K plus, K minus in this catalytic zone, you can choose in this way. So there's an attempt rate, and this reaction only happens on certain regions of the particle that you can encode in such an indicator function that's 0 or 1. And then you have rates that obey detailed balance. And so the particle, so the colloidal particle and the solute particle, they just interact through excluded volume, but one of them is a bit bigger than the other one, or has a stronger repulsion force. So that's how they differ. And outside, you use sort of local detailed balance. And then in computer simulation, you can very easily keep track of the number of conversions of solute particles that are taken from the substrate reservoir and moved to the product reservoir. So this is the solvent flux. And as you change the delta mu, so the difference of chemical potential between the two reservoirs, you see that you go away from 0 and that you reach a certain finite value of the solvent. And you can also measure the force that all these, the force imbalance that these solutes exert on the colloidal particles. So there's also a non-zero force on the particle that you can relate actually to the propulsion speed. So we have now an expression for the propulsion speed. It is just the mobility of the colloidal particle times the magnitude of the force. And so from explicit calculations, you easily find that the solute flux is sort of a tension. You see that this is obeyed very well. There is a prefactor and attempt rate. We have explicit expressions for this. And also for the speed, you find that this is then proportional to this solute flux, as you would expect. And there's a proportionality factor, lambda, that you can sort of determine from these simulations. So for the specific potentials that we've chosen here, you find, for example, that this is on the order of 10 to the minus 7 times the radius of the colloidal particle. So with this sort of explicit model, you can go one step further. So like previously, we already had thought about an effective catalytical model, and this effective catalytical model actually reproduces this more detailed microscopic model. So here we don't keep track of the solute molecules. We just say that there are chemical events with rate kappa plus and kappa minus. And so effectively, each time there is a forward chemical reaction, we take one substrate molecule and we move this to the product molecule. This means that now these rates have to obey local detailed balance. So they have to obey this relationship here, where U is some external potential. And now you can sort of take this model and transform it into evolution equation for the joint probability distribution. So we want to know what's the time evolution of this joint probability distribution, and the first terms that you find, they are well known. So you get sort of a drift term due to this external potential that this active particle is in. And then there is also the translational noise that gives rise to diffusion. These two terms are the translational particle current. There is this diffusive rotational motion that gives rise to this term. And then on top of this, there are these chemical events that translate the particle by the jump length lambda along the orientation. And this is just a master equation that can be sort of interpreted as a finite difference of a chemical current between these two reservoirs. And now we have to pick rates that agree with the rates that we picked for the simulations. So the set of rates, the specific set of rates that we picked here is shown here. So essentially, you have the attempt rate again, this effective attempt rate, the delta mu goes in, and then also the external potentials. If you plug this back into the previous slide, into the local delta balance relation, then you find that this is obeyed. And now the interesting thing is that if we expand this for small lambda, so there's another length scale in this problem, and if lambda is much smaller than that length scale, then we can expand this part here to first order, and then this gives us a term that is exactly corresponding to what we know as active Brownian particles, where there is a constant propulsion speed, and this constant propulsion speed now is given by this expression with parameters that we can extract from the simulations. So with this, I'm already through, so I hope I could convince you that motivate, if not convince you, that chemical degrees of freedom are important and essential for consistent thermodynamic description of active fluids. And so what we have achieved here is really that we have a microscopic model, and that we can show that this microscopic model becomes a very popular model for active matter, active Brownian particles in a certain limit, but we now have an explicit expression for the dissipation, and we can sort of try to see what we can learn from this, and this is actually what Robin is going to talk about. And with this, I thank you.